So the set of videos will basically be supplements to the lesson. I will discuss the examples that we have accomplished in class so far as a review for you, and also a test for me to see whether this type of lecture will work for you. So for the problem solving strategies, a quick recap. So you read the problem carefully at least once, because that's where you get your given, that's where you get your required. And for this is a completely optional step, is to draw a light sketch of the system so that you can imagine it better. Note that this is different from the free body diagram, and the free body diagram is something that you have to draw to facilitate easier determination of your systems of equations. And a slight detail about the coordinate system or the free body diagram is that you have to define your coordinate system and you have to label your forces. For the coordinate system, you're already, well, you're okay with having your standard upright positions Cartesian coordinate system, but then for cases such as the inclined plane, it may be useful for you to slant them a bit. Finally, once you determine the free body diagram, you can get the equations that you need to solve the problem via Newton's second or first law. So for this case, you have forces in the x direction and you have forces in the y direction. All you need to do is add the both of them. Finally, once you do that, you can already solve the systems of equations for you to determine what's needed for the problem. So let's try for the first example, the traffic light at rest. So in here, it's a static equilibrium problem. The traffic light weighs a certain number of newtons from a vertical cable tied to two other cables. So when I'm going to discuss items like this, so that it's rather short and easy to download, I'll keep the discussion short, and I won't solve the actual values anymore. I leave that up to you. But what I will give you are the values before plugging in what's given. So in here, since it is in static equilibrium, the sum of forces should be equal to 0. That means the component of force in the x direction should be 0 as well as y. Starting with the x direction, you notice that it's t2 cosine theta 2 minus t1 cosine theta 1, and that came from the decomposition of your free body diagram vectors. So what I decompose here are the vectors t1 and t2. And using this as a transversal and using this as a parallel line to the horizontal on top, you determine this to be theta 1 as well. From there, you can decompose the vector of t1 by t1 sine theta 1 and t1 cosine theta 1. For t2 on the other hand, you have t2 cosine theta 2 and t2 sine theta 2. So theta 2, this is also theta 2. And if you just look exclusively at the x direction, you notice that t2 cosine theta 2 points to the right, so that's why it's positive. And t1 cosine theta 1 points to the left, that's why it's negative. And since the sum should be equal to 0, all you need to do is isolate t2 to give you this equation. So now you're done with the x direction. Basically, you're going to need this when you're trying to solve the forces in the y direction. Okay? In the forces in the y direction, by looking at the diagram, you can see that t1 sine theta 1 and t2 sine theta 2 both point upward. That means it should be positive in your sum of forces in the y direction. Whereas t3 is the only force that points downwards, and that's the force that counterbalances the upward forces provided by the upper cables. Now, T3 may be a bit unique because it's insufficient for you to just rely on a single free body diagram for this problem. Note that the free body diagram for this problem is reliant on the junction, basically where the three strings meet. But then to be able to get a working definition for T3, you need the free body diagram of the stoplight. And for the free body diagram of the stoplight, you only have the tension pointing upwards and gravity pointing downwards. It may be a bit peculiar for you to notice that T3 for the stoplight points upwards, but T3 for the junction points downwards. That's because the T3 that points upwards acts on the stoplight, whereas T3 that points downwards acts on the junction. These two forces form an action-reaction pair. So that's from Newton's third law. So now that we know that this should be balanced by saying that the forces should be balanced, we know that T3 is just equal to mg. From there, You can already plug the values not only of mg but also of t2 from the previous equation. So using this, you end up with this equation. Simplify yung sine theta 2 over cosine theta 2, and you'll get this term. And the goal here is to get t1, and all you need to do is factor it out and divide both sides with its coefficient, giving you this answer. Now, it's up to you whether you want to plug in the values at this point, but then, believe me, you'll just get the same answer, okay? So if you want to answer similar problems to 4.6, you can pause the video and check these examples. They're at the end of the chapter of your book. The next example, I skipped a few ones, is the runaway car, because this is the first example wherein you have an incline, or actually this is already an example of an incline, and also the first example wherein from the incline it will fall down. So a car of mass m is on an icy driveway inclined at an angle theta. Icy driveway to indicate that you have a frictionless surface. You have to determine the acceleration of the car assuming the incline is frictionless, right? So first things first, you make your free body diagram. Sorry if it's a bit slanted, but then what's important about the normal force is that it's supposed to be perpendicular to the surface. So it's not really drawn in the best way. And the other force that governs this system or this movement of the car is just gravity. And we've discussed this kind of vector pattern before, and you should be able to realize that this will not balance the forces. Forces in the y maybe, but forces in the x, you'll be forced to have a non-zero sum of forces. This is what I said when I meant a while ago that you have to choose your appropriate coordinate system. It's much more convenient for us to slant the coordinate system because this Fn will basically be the basis of our solution. And the normal force, Fn, will need some force to balance it out because you don't expect the car to be jumping around on the surface. And you expect that force to come from one of the components of gravity. So, how did we get this to be theta? Basically, you just follow your trig. This is a right triangle, the small one here. If this is theta, this should be its complementary angle, 90 minus theta. And this should also be perpendicular because you form vertical angle pairs. You know this to be perpendicular because of the definition of the normal force. Then this should be perpendicular as well. And if this is 90 minus theta, then this should be theta. So the force that balances out the normal force is basically the cosine component of gravity. And the one that provides the non-zero force, which ultimately leads to its acceleration, is mg sine theta. So the car won't rise from the surface. The car will accelerate along the surface. This is your equation in the y direction. And that basically provides your normal force. Now, what gives us our acceleration downward basically is mg sine theta. And if we're looking for the acceleration of the car as it rolls down the hill, you have this equation. All you need to do is cancel out m. And there's something interesting about this result, which will be described in the remarks. First one is that acceleration is independent of mass. This is consistent with Galileo's findings when he dropped a ball and a feather down a building. It's a thought experiment, but then this further confirms it. So let's work with extreme cases. What if theta is equal to 0? That means you won't have an incline, the surface will be flat. The car won't accelerate because at that point in time, it's just going to be resting on the surface. Mathematically, when theta is equal to 0, you have an A is equal to g sine 0, which is also 0. And let's work with the other extreme. If theta is equal to 90, the surface becomes a wall. So you expect it to be like the wall of a building. That means the car won't latch on the surface anymore and it will experience free fall motion because it won't stick to the wall. Mathematically, that means A is equal to g sine 90 degrees, but sine 90 degrees is just 1, so A is equal to g, the conditions for free fall. So if you want to answer similar problems to 4.9, I invite you to check example 4.7. We already did this. It's still an incline problem, but the only difference is it's in equilibrium. And you may wish to check problem 4.2 4.27, which is a two-body system in equilibrium. I also gave you the homework 4.21 to answer, and we'll discuss it in a later video. It just goes to show you that you can solve problems like this. Next. Example deals with weighing a fish in an elevator. This is the spring balance problem, and also the last example for this video. So a fish is weighed using a spring scale. Imagine the fish to be the triangle, and is attached to the ceiling of an elevator. And the elevator is moving with an acceleration of a. So we have to determine the apparent weight measured by the tension of the string. Now, whatever tension that the string will experience, the spring scale will experience, and the spring scale converts that tension to a measurement of weight. So you have to determine the apparent weight measured by tension. Basically, you're supposed to get the tension of the fish when the elevator is going up and going down. Okay? So, because an elevator can either go up, and we've experienced it before, when you go up, you'll feel heavier. When you go down, you'll feel lighter. And we'll mathematically verify that that is the case. So in the free body diagram of the elevator, of the fish, it's just T in the upper direction and mg in the lower direction. It's standard, you've seen it before, but the main difference is the sum of the forces isn't zero. Because what happens is actually that fish is accelerating upwards if it's positive. So how will this change the equation? Basically, if the acceleration is positive, let's work with the first case. That means your acceleration vector points up, then that means acceleration is positive. Then you'll have this equation, which you can then isolate t to get this. T is equal to mg plus a. Usually your weight is just equal to mg. But since the elevator is moving upwards, this acceleration that's positive actually contributes to your apparent weight. That's why you feel heavier as the elevator goes up. Okay? Next, let's work with the other case. What if the elevator is moving downward? That means the acceleration vector is negative, so you expect the ma term to have a negative sign. And again, the same step, you have to isolate t. And you'll end up with this solution, or this equation. I'm sorry, that should be minus a. Please correct it. So that's g minus a. And that means it's supposed to be lighter. Or whatever tension you're feeling is actually lighter. Alright? So for the next video, I'll discuss Atwood's machine and forces of friction. Thank you for listening.